Your web scraper isn't broken, it's under-engineered. It works in testing, passes health checks, and returns HTTP 200, but quietly collapses once real traffic, scale, and anti-bot systems come into play. You're on the Proxy-Seller channel. I'm Mark, and today we're talking about why web scraping fails in production and the top engineering reasons teams underestimate until it's too late. Scraping does not equal script, it's a distributed system. By 2025, web scraping had clearly moved beyond controlled environments. Production pipelines were already interacting with dynamic, personalized websites, protected by adaptive anti-bot systems and strict rate limits. Multiple industry and academic studies published throughout 2025 showed that even relatively simple crawling tasks now behave like distributed systems, with concurrency, retries, partial failures, and non-deterministic responses. A modern scraping pipeline consists of several interconnected stages: requests, retries, parsing, ingestion, and downstream analytics. Research in data engineering consistently demonstrated that most data quality issues were detected after ingestion, not during collection. By the time teams noticed missing, delayed, or malformed data, the requests had already been executed, resources consumed, and request-level context lost. The consequence was structural rather than technical. Many teams continued to debug scraping as application code, looking for bugs in scripts or selectors. But the real failures emerged at the system level, from interactions between components under real load. By 2025, it was clear anything that scales behaves like a distributed system, and scraping was no exception. Reason number 1. Testing does not equal production. In many production cases observed in 2025, web scraping pipelines didn't fail because of faulty code. They failed because testing environments did not reflect real operating conditions. Test setups usually involve a small set of URLs, predictable responses, low concurrency, and little exposure to anti-bot systems, which creates an illusion of stability. Production environments introduce conditions that rarely appear during testing: concurrent request execution, retry cascades and traffic spikes, rate limiting and throttling, dynamic or personalized content, and adaptive bot detection mechanisms. This is where pipelines that looked reliable in staging begin to degrade. The result is a false sense of confidence. Scrapers pass all tests, deploy successfully, and keep running, but data quality erodes through partial, delayed, or inconsistent responses. The system doesn't crash, so issues go unnoticed. This structural gap between testing and production is the first reason most web scraping systems fail at scale. Reason number 2. Scale exposes structural weaknesses. At small volumes, scraping systems often appear stable, but once traffic scales, underlying architectural weaknesses surface. This isn't a coincidence, it's a property of distributed systems. Under real scale, pipelines begin to experience race conditions between requests and parsers, CPU and memory contention from parallel execution, retry amplification that multiplies failing requests, and extraction drift as page structures vary across responses. These issues don't usually cause outages. Instead, they slowly reduce throughput and data quality. A small failure rate at the request level compounds into significant loss downstream. Scale doesn't introduce new problems, it exposes assumptions that never held under load. Reason number 3. Anti-bot is an operating condition, not an error. By 2025, it became clear that most large-scale platforms no longer rely on hard blocking as their primary defense. Instead, anti-bot systems continuously observe and classify behavior over time. In practice, this means scraping pipelines don't get blocked immediately, they get degraded. Full pages are replaced with generic HTML, structured data is partially removed, responses are delayed or rate-shaped, and content varies based on perceived risk. From the system's perspective, everything still looks up. Requests return responses, status codes remain successful, and pipelines keep running. But analytically, the data is no longer reliable. Treating anti-bot mechanisms as edge cases leads teams to misdiagnose the problem. In reality, they are a permanent operating condition, and one of the main reasons scraping fails silently at scale. Reason number 4. Success codes don't mean usable data. One of the most common misconceptions in scraping systems is equating technical success with analytical success. An HTTP 200 response only confirms that something was delivered. It says nothing about whether the data can actually be used. In production scraping, requests often succeed technically while failing analytically. Responses contain HTML instead of structured data. Critical fields are missing or incomplete. Data arrives too late to be useful, and content is altered based on bot classification. Because these failures don't trigger errors, pipelines continue running and dashboards stay green. But downstream systems, analytics, models, and decision logic operate on degraded inputs. The gap between delivery and usability is a major reason scraping systems lose value without ever appearing broken. Reason number 5, observability starts too late. In most scraping architectures, observability begins after ingestion, once data has already been stored, transformed, or aggregated. At that point, individual requests are no longer visible. This creates a structural blind spot. Request-level failures disappear once data is ingested. Retries and partial responses leave no trace, and root cause analysis starts after the damage is done. As a result, teams monitor pipelines, not collection. Systems appear healthy, while data quality quietly erodes upstream. When observability starts too late, failures are invisible by design, and scraping systems fail without ever triggering an alert. The pattern? Scraping pipelines degrade, they don't fail. Taken together, these 5 reasons point to one consistent pattern. Web scraping systems rarely fail through a single error or outage. Instead, they degrade gradually, request by request, response by response. Pipelines keep running, dashboards stay green, but underneath, data becomes less complete, less timely, and less reliable. Costs increase through retries and overhead, while value quietly decreases downstream. This is why scraping failures are often discovered late. Not when something breaks, but when business outcomes drift. Understanding this pattern is critical. Once teams stop looking for crashes and start looking for degradation, the real problem becomes visible and solvable. By 2025, one conclusion became unavoidable. Web scraping cannot be treated as a script or a one-off task. It behaves like infrastructure. Failures don't come from individual bugs, but from how the system is designed, observed, and scaled. When scraping pipelines are treated as infrastructure, priorities change. Observability moves upstream, validity matters more than volume, and proxies become part of the data stack, not just a network utility. This shift is what allows teams to scale data collection without losing control or trust in their data.